We've talked about a lot of different derivative rules at this point. We've talked about the product rule, the quotient rule, the chain rule, derivatives of exponentials and e to the x, and logarithms and natural log of x. In this section, we're going to talk about implicit differentiation, which is sort of an extension of the chain rule and sort of its own different thing. But before we start to talk about what implicit differentiation is, I want to talk about what it's not, kind of what makes implicit differentiation different than the types of differentiation that we've done so far. So the function we'll be working with is 3x squared plus y minus 2 is equal to 0. Now, if we were to use explicit differentiation, which is what we've done all along here, it's how we've been taking derivatives the whole time in our class so far. There's really two steps to it. First, you need to solve for y. And most of the time, we haven't had to do this step because most of our functions are always y equals f of x, where we already have y by itself. But if we don't have y by itself, kind of like we don't here, we need to get y by itself. So I'm going to subtract 3x squared from each side. I'm going to add 2 to each side. And that will give me y equals 2 minus 3x squared. So okay, there's y, and the reason that this is called explicit differentiation is because y now is explicitly a function of x. It is a function that is written only in terms of x. So here I have 2 minus 3x squared. Once I have solved for y, second step, we take the derivative. So this includes using any sort of derivative rule that we might need. So we might need the product rule or the quotient rule or the chain rule. Here we just need the power rule. Derivative of 2, that's just going to be 0 since it's a constant. Derivative of negative 3x squared, that should be minus 6x. So this is how we've been taking the derivative all along up until this point. Implicit differentiation sort of takes these two steps. It sort of takes these two steps and actually kind of flip-flops them around. So what I'm going to do first when I use implicit differentiation, the first thing I'm going to do is I'm actually going to take the derivative first. And the hint I'm going to give here, or the reminder I'm going to give here, is we need to use the chain rule for y. And the reason I need to do this here is I'm thinking about, I wrote this earlier, I said y is equal to f of x, which if I actually write out what this means, this says y is a function of x. So if y is a function of x, I have to use the chain rule when I take the derivative of that term. So I'm not going to actually change this expression at all. I'm just going to leave it as 3x squared plus y minus 2 is equal to 0. And I'm going to take the derivative of this whole equation without solving for y first. So the way I'm going to do that, we haven't used this notation a ton, but I'm gonna say d over dx 3x squared. So what this says take the derivative of 3x squared. So take the derivative, and I should say take the derivative with respect to x here. So take the derivative with respect to x of 3x squared, plus I'm going to take the derivative with respect to x of y, and that one's going to be a little bit different. We'll talk about it. Minus the derivative with respect to x of 2 equals the derivative with respect to x of 0. And I'm just going to work my way kind of down the line here and take the derivative of each one of these terms. When I have the derivative of a term that is written only in terms of x, so here I'm looking at just 3x squared, we're going to take the derivative just like we normally would. So we have to use the power rule there. Derivative of 3x squared, that should be 6x. So that part's really no problem. Plus, this is where things get a little bit different. Here I want to take the derivative with respect to x of y. But I'm thinking about, again, y is a function of x, and if y is written as a function of x, I'm taking the derivative with respect to x. I have to use the chain rule. So the way I'm going to do this, the way I would encourage you to think about this, I can think about this as y to the first power here. And I would encourage you to think about this almost as if it were just x to the first power. What would x to the first power? What's the derivative of that term? Just be 1. So the derivative of y to the first will also be 1, but I need to remember my chain rule. Remember the ending part of the chain rule always says, and you multiply by the derivative of the inside part. So I'm also going to multiply by, you can either say y prime, or you can use the notation dy over dx, just depending on your preferred notation. I think it's actually a little bit easier to use dy over dx just because we will have functions that have y and y prime, and I always worry that it's going to be easy to mix those two up. So I like dy dx. I think most students prefer y prime just because that's the notation that we use most often. So I'm going to use y prime here. And one thing I actually just want to make very clear here, y prime, this up above, I wrote that as y to the first. I just want to make sure that that's a 1 and not a prime. So here I have y prime. Okay, so we'll talk more about terms like this later, but really it's just the derivative of y, which is 1, times y prime for my chain rule. That's really what I'm doing here. Okay, let's keep going. Derivative of 2, well, 2 is a constant, so the derivative of that is 0, so we'll say minus 0 is equal to, over here, the derivative with respect to x of 0. Again, 0 is just a constant, so derivative of that term will just be 0. So I really have 6x plus y prime is equal to 0, if I kind of clean that up a little bit. So that's my first step, is just to take the derivative. And granted, yes, the derivative is a little bit different because we have to use this chain rule for y, but I think it's something that will start to come naturally as we do more and more examples. So okay, we'll take the derivative. Remember I said earlier, I said implicit differentiation sort of takes these two and switches them around. So instead of solving for y, though, I don't have a y. Sometimes I will have a y, but I don't really want to solve for y. I want to solve for y prime here. Because remember, at the end of the day, I'm trying to take the derivative. That's what I want. I want y prime. So here, this one's easy enough to do. I'm going to subtract 6x from each side. So y prime equals negative 6x. Here is my derivative using implicit differentiation. And look at this. I have exactly the same derivative using explicit and implicit differentiation, which is really cool. This is very reassuring to see that we end up with the same derivative no matter what. So you might now be asking the question, well, okay, if we end up with the same derivative, why would we use implicit differentiation over explicit differentiation? Why do we have to learn this whole other method of differentiating functions when I have explicit differentiation that seems to work just fine for us? So the reason this is so helpful is because we can do cool calculus stuff now with implicit differentiation. It's helpful for things that are not functions. So implicit differentiation is useful for relations that are not functions. So if I look at this equation right here, so here we're going to use implicit differentiation to find y prime and then evaluate y prime at the point that's given. Here I have y squared minus y plus 4x is equal to 0. If you were to type this into, say, like Desmos.com or something, this actually isn't a function. you would see, I'm not sure exactly where it would sit, but you would see a parabola that opens sideways. You would see something that looks like this. And then if you drew your vertical line, you would see, okay, it intersects here and here. This is not a function. But perhaps I still want to be able to talk about things like slope of the tangent line at a certain point. So here, if I want to talk about slope of the tangent line, I want derivative. And if you look at this, this is going to be a very difficult equation to solve for y. I'm not saying you can't do it. You absolutely could. But you would end up with actually two different functions. You would have to use the quadratic equation, and the resulting functions that you end up with would be really ugly and really messy and just generally very difficult to work with. So it's much easier in a case like this to use implicit differentiation because it just makes the process of finding that derivative so much easier. So I am going to use implicit differentiation here to take the derivative of this function first. So first I'm just going to find y prime. So I'm going to take the derivative of each one of these terms, and actually let me just write it out. Y squared minus y plus 4x is equal to 0. I want to take the derivative with respect to x of both sides of my equation. So let's take each term one by one. First of all, derivative of y squared with respect to x. Well, the derivative of y squared, pretend for a moment that that's just x squared. Derivative of x squared, you would tell me, is 2x. Derivative of y squared then should look like 2y. But I need to remember my chain rule for y, because y is a function of x. So I need to multiply that by the derivative of the inside part. The derivative of y in this case, well, derivative of y is just y prime. So I'll have 2y times y prime, or times dy dx if you prefer that notation, minus derivative of y. We looked at this example earlier. Pretend again, just for a moment, that derivative of x, no, derivative of x is 1, derivative of y I'm also going to say is 1, but again, chain rule for y. So I need to multiply that by y prime. Derivative of 4x, here this term is written only in terms of x. There is no y for this particular term, so I'm just going to take the derivative like I normally would. So the derivative of 4x will just be plus 4, and on the other side, derivative of 0, that's just 0. So if I clean this up a little bit here, I've got 2y times y prime minus y prime plus 4 is equal to 0. So at this point, I've taken the derivative, which I think is kind of the harder part of this. This is the really new part of it. After that, I need to solve for y prime, and you may run into situations like this where actually it looks like I've got more than one y prime. So I've got two terms that have a y prime. So I'm going to take everything that does not have a y prime, which is this plus 4. I'm going to move that over to the other side. And essentially, I'm trying to get the terms that have a y prime. I want those on one side of my equation. The terms that do not have a y prime, I want to move those over to the opposite side of the equation. So if I subtract 4, 2y, y prime minus y prime is equal to negative 4. Now these two terms both have a factor of y prime, so I can factor that out. I can say y prime, that'll leave me with 2y minus 1 is equal to negative 4, and I'm trying to isolate y prime, so I'm just going to divide by 2y minus 1. Y prime equals negative 4 divided by 2y minus 1. Here is my derivative. Now notice we have something kind of odd happening here where our derivative actually has a y in it. And you'll see this a lot with implicit differentiation, where your derivative, since you didn't begin with a function of x, perhaps your derivative is not a function of x. So here we may end up with an equation that depends both on x and y. So if it depends on both x and y, that means if I want to evaluate y at the point that's given, I need both an x value and a y value. So I'm actually going to need both an x value and a y value in order to evaluate the derivative and to find y prime. So I'm just going to take the x value 0, I'll plug that in for x, the y value 1, plug that in for y. In this case I only have y. So y prime equals -4 divided by 2 times y is 1 minus 1. I'm just evaluating this expression then. So -4 over 2 minus 1 gives me -4 over 1, which is -4. So there is my derivative, right? Because this is just y prime. I'm evaluating y prime. So this is my derivative. This is also the slope of the tangent line is -4 at this point 0, 1 if I'm looking at this relation. Remember, it's not a function. If I were to look at the graph of that relation, the slope of the tangent line to that graph at 0, 1 would be -4. All right, let's look at one more example here in this video. And this one's going to be a little bit trickier. Here I have 2x cubed y minus x cubed plus 5 is equal to 0. I want to find y prime and then evaluate y prime again at this point. -1, 3. So I'm looking at this here. So again, let's just rewrite our problem. 2x cubed y minus x cubed plus 5 is equal to 0. And I want to take the derivative of both sides with respect to x. This term right here is the one that's going to give us the most trouble. This is the one that's actually going to be pretty tricky. Because if I look at that term, I have 2x cubed times y. And I went out of my way to say times y. What I really have is 2x cubed times y. This is a function of x. And remember, I also want to think about y as a function of x. So I have a function of x times a function of x. This term right here requires the product rule. We have to use the product rule for that term. And this is something I think that's really sneaky and really easy to overlook. Anytime you have a power of x times a power of y, and we're taking the derivative implicitly, we're going to have to use the product rule every single time. So that's just something that you're going to have to keep an eye out for. You want to look out for that power of x times that power of y. Luckily, though, the product rule is it's gonna work pretty much exactly the same way that it has all along. We just need to remember that we're using the chain rule when we take the derivative of this y term. So let's see. I'm going to take this slowly. Derivative of 2x cubed. And actually, you know what? Let's do this. Because this is such a new idea, I'm going to call this f and I'll call this g. So f is equal to 2x cubed. G is simply y. So f prime, derivative of 2x cubed, that will be 6x squared. G prime, derivative of y, we would say is 1. But again, I'm using the chain rule because I'm thinking about y as a function of x, so 1 times y prime, or simply just y prime. If you just want to jump down to here for these, I think that's perfectly fine. So my product rule says f prime times g, so I'm going to take 6x squared times y, plus f times g prime, this will be 2x cubed times y prime. So here's my product rule again. This is f prime times g plus f times g prime. That's what's really happening here. So anytime you have, again, a power of x times a power of y, you're going to have to use this product rule. So this one term is sort of breaking up into two after I take the derivative. The rest of the problem is a little bit more straightforward. I think it's a little bit easier to manage here. Derivative of negative x cubed, there is no y, so I take the derivative like I normally would. That should be minus 3x squared. Derivative of 5, that is just a constant, so I'm going to write plus 0 there. You don't have to write plus 0, but I just want to show what's happening to every single term. And then on the other side of my equation, derivative of 0, well, that's just 0. So I have 6x squared y plus 2x cubed y prime minus 3x squared is equal to 0. So I've got my derivative. I now need to solve for y prime. I want to get y prime by itself. So let's see, I'm going to subtract these two terms or add those two terms over to the other side. So 2x cubed y prime is equal to 3x squared minus 6x squared y. And then divide by 2x cubed, divide by 2x cubed. So let's see, y prime is equal to 3x squared minus 6x squared y divided by 2x cubed. I see that I can factor that numerator, and it's just going to bother me if I don't. So I'm going to factor out particularly x squared because I see, hey, I can cancel that with a factor of x in the denominator as well. So x squared times 3 minus 6y divided by 2x cubed, we can cancel an x squared. That'll leave me with 3 minus 6y divided by x. There is my y prime. So the end of the problem, that second step, really isn't a whole lot of new stuff. I don't want you to get worried about that second step. That's all just algebra. I think that finding the derivative, this is the new stuff, because we need to kind of think about y as a function of x, and we need to sort of train ourselves to think about y as a function of x, which is a really new idea. Lastly, I'm going to evaluate my y prime, so I'm evaluating this guy at the point negative 1, 3. So I'm going to take the x value, negative 1, plug that in for x, the y value 3, plug that in for y, and solve for y prime. Whoops. So y prime equals 3 minus 6 times, I already forgot, 3, divided by x was, I already forgot again, negative 1. Let me write it down. Negative 1, 3. So divided by my x value of negative 1. And I'm just evaluating this expression here. So I have 3 minus 18 divided by negative 1. This is negative 15 divided by negative 1 gives me a positive 15. So again, remember what we're solving for is the derivative y prime. So if I was to look at the slope of the tangent line to this relation, if you were to graph it, you'd probably see a really funky looking graph. But if I was to look at the slope of the tangent line to this graph at this point, I would have a slope of positive 15. So even though I'm using this new method to find my derivative, to use implicit differentiation at the end of all of these problems, I still have the same thing I've always ended up with. I'm still ending up with a derivative, and it still tells us the same piece of information. It still tells us slope of the tangent line.